So today I am starting with the frequency sampling FIR filter. All right. The point is that we can design the FIR filters using a non-recursive way also. If we consider the impulse response of the system to be G naught by capital N, right? It is a causal response because the response is 0 previous to small n equal to 0, right? And it also exists only for finite value of small n, finite duration from 0 to capital N minus 1. So finite. So that means the impulse response is finite. So this is the case of a FIR filter. But let us see how it is the recursive approach. Now, if I take the Z transform, my Z transform of the previous impulse response will be this. I can put the Z transform in this general equation, G naught by capital N, P equal to 0, sigma going from P equal to 0 to capital N minus 1, Z to the power minus P. All right. Then if I know that this is a GP series, if I put the sum of this GP series to be G naught by capital N, 1 minus Z to the power minus N divided by 1 minus Z to the power minus 1. I separate out the two smaller transfer functions like this, same equation, but two components separated out. I call one component as the comb filter, the other component as the resonator. All right. Now, this is the structure of the this is the structure of HZ, the transfer function, right? So this comb filter is basically a feed forward part, and the resonator is basically a feedback part of this overall system. Now, this is the structure. Now, I can see that this becomes the feed forward part, and this becomes the feedback part. All right. Now, let us take an example. I was about to take an example where I will choose the value of capital N to be 8. So this equation will be reduced. The comb part will be 1 minus Z to the power minus 8 divided by 8, and the resonator part will be G naught divided by 1 minus Z to the power minus 1. I take the value of N to be 8 and G naught to be 1. So my transfer function comes out to be 1 minus Z to the power minus 8 divided by 8 and 1 minus Z to the power minus 1. Now this is the structure. If I take the example of this input xn is 1 at n equal to 0 and otherwise 0. If I take this input, what should be my output at various points? Now my output at this point will be 1 by 8 because this 1 by 8 scaling factor is there because of this 8 in the denominator. So the amplitude will be reduced to 1 by 8, and first one will go straight way because it is not going through any delay element. So the first sample will be 1 by 8, and rest it will be passing through because it is a delay line of 8 units, right? Next sample will come after 8 units of time. Otherwise, you will get 8 0, 0, 1, 2, 3, and up to 7, and 8th will be your minus 1 by 8 because it comes through this next one comes through the one that will be held here will come after multiplication with minus 1, right? So this is the output that we will get at this point. At yn, this is the output. All right, you can verify this output. There is no problem. At yn, what you will get at yn? At yn, you will get 1 by 8, 8 times 0, 1, 1, 2, 3, 4, 5, 6, 7, and 8. 8 samples of ones, right? And because this yn is also being forwarded, is being fed back, right, with 1 unit of delay. So the waveform at this point will appear to be like this because this is yn. So naturally it will be delayed by 1 sample. So this is the point that why I took the example here of capital N to be equal to 8 is that if you look at the output yn, if you look at the output, this is the output. This portion looks like a comb जिससे हम कंघी करते हैं. So it looks like a comb. That's why the name is a comb filter. The output is output looks like a comb. All right. So that's why the first part is a comb filter. That's why it is called a comb filter. All right. And how many in this transfer function? If you look at the transfer function, how many zeros are there? You have 8 zeros. Let me go to the next slide. So this is my comb filter transfer function. What is comb filter? Comb filter is the first part. That is the this is the comb filter. 1 minus z to the power minus n divided by n. Now let us analyze the comb filter part. So what is the transfer function of comb filter? 1 minus z to the power minus n divided by n. And if you take the frequency response, you all know that how to get the frequency response. Just replace that with e to the power j omega. So you will get hc omega equal to 1 minus e to the power minus j omega capital N divided by n. And you also know that how to separate out the phase part and the magnitude part. To the maximum value of the exponent, take out the half power. So you will be able to get the phase part and the amplitude part separately. All right. Now the magnitude part is shown in the next slide for n equal to 8. So this is I will come to this part, no problem. So what is hc omega? Hc omega is the frequency response. And what is mod of hc omega is the magnitude response. For n equal to 8, the slide is on the next, the waveform is on the next slide, but I will come to that. So hc omega, this is hc omega, has capital N zeros. This is very important. Why it has got capital N zeros? It is very obvious from the numerator polynomial that there are n zeros because the power of z is n. Right, so there will be n zeros, and these zeros are equally spaced over the frequency range 0 to 2 pi. These zeros, capital N zeros are there. These are equally spaced on the over the frequency range from 0 to 2 pi because the magnitude response resembles a comb. This filter has become known as a comb filter. Now this is the frequency response. This is the same equation. And why I have put 8 here? Because I am just I'm carrying on with the example of capital N to be equal to 8. So this is my magnitude response. This is my frequency response of what? Of a comb filter with capital N equal to 8. Now, if I draw the magnitude response, if I take the mod here and I draw the magnitude response, because there are 8 zeros, and these 8 zeros are separated with equally spaced intervals from 0 to 2 pi. Let's say this is my omega equal to 0, and it goes like this, it goes like this, it goes like this. This completes 2 pi. So 8 zeros, if I take the example of 8 zeros I have to place on the unit circle, on the circle, right? On the circle, I have to place 8 zeros and equally spaced 8 zeros. Now, what is the spacing between the between each zero? The spacing between each zero is given by 2 pi by capital M. If I take the example of capital N to be equal to 8, the first zero will be at 0, this point. The second zero of the, what is a zero? A zero means the transfer function goes to 0 for that particular value of z. So first zero will come at this point, second will come at 2 pi by 8, 2 pi by 4, and so on. All right. So 1, 2, 3, 4. You see the zeros. 1, 2, 3, 4, 5, 6, 7, and 8 zeros will come. Next, this zero will be counted for the next cycle. All right. So there will be 8 zeros. And in general, for capital N, how many zeros will be there? capital N zeros will be there, and what is the spacing between the zeros? Spacing will be capital N, 2 pi by capital N. Now, if you look at the pole zero pattern for the comb filter, can be obtained using the transfer function. This is the transfer function of the comb filter. Now I can do little modification. I can take out z to the, I can multiply the numerator and denominator with z to the power n. I will get this part. All right. And I know that if this is the polynomial, then I can factorize this. The factorization will result into 1 minus e to the power minus j 2 pi by n into k z to the power minus 1. The above equation explicitly indicates that there are capital N equally spaced zeros over the unit circle with the first zero at z equal to 0, right? So that's what is shown here. The zero, there will be, for capital N to be equal to 8, there will be 8 zeros on the unit circle. This is for the case of comb filter only. This is the pole zero pattern for the comb filter. And since the system has to remain neutral, there will be 8 poles, equal number of poles will be there, but those poles will exist at origin. The pole or a zero even at origin do not contribute anything to the transfer function. All right. So these are the positions of 8 zeros if I take capital N to be equal to 8. This is the case of comb filter. Please remember that. Pole zero pattern for the comb filter. And this is the magnitude response of the comb filter, and it resembles a comb. That's why this is known as a comb filter. This type of filter is known as a comb filter. All right. Now, let's come to the second part of the overall transfer function. What was the second part? The second part was the resonator part. This part. G naught by 1 minus z to the power minus 1. Let's come to this part now, and let's see what is the role of this part. Now h r naught z, which is the resonator transfer function, this r will be in the subscript basically. h r naught z is the system function of a resonator or a filter. Now this is also a filter, but we call it as a resonator. Why do we call it as a resonator? Because it has pole. If you look at the transfer function of this, the transfer function is g naught by 1 minus z to the power minus 1. G naught, if we take as 1, what is the transfer function of resonator? 1 over 1 minus z to the power minus 1. It has got only one pole. And what is the location of that pole? Z equal to 1. So at z equal to 1, on the point is that the pole is at the unit circle. So once the pole is on the unit circle, it is very liable to be unstable. Once the pole goes out of the unit circle, the system will become unstable immediately. Since this pole is not strictly within the unit circle, the filter is not stable. That's why this is called a resonator, because the system may oscillate here. When this resonator is cascaded, but this is in itself a resonator filter of this nature is unstable. There is no doubt about that, because a pole on the unit circle or outside the unit circle will lead to an unstable system. Now when this but the question is that when this resonator is in cascade with comb filter, what happens? The zero of the comb filter located at z equal to 1. What is that zero? This zero. Z equal to 1. This is the zero, and the pole is also here, right? This zero is coming from where? This zero is coming from the transfer function of the comb filter. From where the pole is coming? The pole is coming from the transfer function of the resonator. All right. Now, when this resonator is cascaded with the comb filter, the zero of the comb filter located at z equal to 1 cancels the resonator pole, making the combination stable. That's very important. The combination of the comb filter and the resonator becomes stable because the pole of the resonator is cancelled by one of the zeros of the comb filter. Now the transfer function of this two-stage filter. So this is the transfer function. Again, we have already seen this transfer function. Okay, so this is the same equation. This is the same equation of the two-stage filter. What is the two-stage filter? The first stage is the comb filter. The second stage is the resonator. All right, let's go further. Now, for n equal to 8, mod of h omega, which is the magnitude response, has a maximum at omega equal to 0, right? It will have a maximum at omega equal to 0 equal to g naught and is equal to 0 at 2 pi k by n. We know that it will go to 0 for 2 pi by n, right? Magnitude response of, this is the magnitude response of comb filter plus resonator. Please mind it, this response is only of the comb filter, which is a comb shape. But when you cascade a comb filter with a resonator, this is the magnitude response. What does this magnitude response say? The magnitude response says that it has a maximum at omega equal to 0, which is equal to g naught, and is equal to 0 at 0. We know that zeros will occur at 2 pi by capital N. And k is an index which gives us first 0, second 0, third 0, and so on. That's what is the role of the index k. But now, this is for the case of the first order resonator. What is the first order resonator? First order resonator means this is first order resonator. Only one pole is there in this resonator. That's why this is a first order resonator. But if we consider a second order resonator filter also, let's consider that. Now let us consider a second order resonator whose coefficients are real valued and the poles are situated at the following zeros locations of the comb filter. We consider a second order resonator, right, whose coefficients are real valued, but the poles are situated at the following locations of the comb filter. Where are the poles located for the resonator? If. Now, this is my first pole, right? If the system is a first order system, now this will be complex conjugate pair of poles. E to the power j pi by 4, e to the power minus j pi by 4. If I consider a second order system in such a way so that these two poles are complex, I will take one lecture, in the coming, whenever a system has a complex conjugate pair of poles, right? What is the importance of that system? I will explain you that part maybe in the coming one or two lectures, but let us take the case straightway as it is, that these two poles are complex conjugate pair of poles. Now this 0 is cancelled with this pole, this 0 and this 0 is also cancelled with these two poles. This is not actually 8. How many poles will be remaining? Only 5 poles will be remaining now. 5 poles will be at the origin because it is n equal to 8. 5 poles will be at the origin. I will correct it. This is not 8 poles, this is 5 poles. 5 poles will be at the origin and 3 poles will be on the unit circle to cancel these zeros. Now, the system function of the second order resonator. Now, system function of the second order resonator can be written in parallel form. What is the system order? What is the system for the resonator? Let me show you the second. Okay, this is the system. It is g naught by 1 minus z to the power minus 1. This is a first order resonator. But if you are considering second order resonator system, in that case, and that too, we are considering a parallel structure. How do we get a parallel structure? Once we take the partial fractions and there will be plus this smaller transfer function, which is a first order transfer function, will be in parallel with another transfer function which is given by g minus 1, because if you see here, this is one pole, this is another pole, this is complex conjugate pair. So that is why the notations are also selected like this: g1, g of minus 1. It is this system for smaller system, it is the second smaller system. When the two systems are in parallel with each other, this becomes the second order system. Now the system function of the second order resonator can be written in parallel form, as it can be written like this. This procedure can be generalized to include each second order resonator cancelling a pair of zeros of the comb filter. Now we can generalize the this is a second order resonator system, but we can generalize for any third order, fourth order, and so on. We can define an index k going from 0 to capital N minus 1, gk divided by 1 minus e to the power j 2 pi k divided by z. So this part is the resonator part of higher order. We can put the smaller resonators in parallel to get a bigger resonator, higher order resonator, and this part is the comb filter. So this becomes my overall filter, which is a combination of the comb filter and the resonator. All right. Now, and I can put the structure like this, a general structure like this. This is what? This part is my comb filter. This is my input, 1 minus z to the power minus n divided by 1 divided by n. This is my comb filter. This is my first order resonator, second order resonator, and so on. Higher order resonators. Right? GK I can define like this. So this is the structure of the filter that will be resulting from comb filter and resonator combination. Now, if the comb filter is followed, please try to understand that. If the comb filter is followed by a recursive network, what is the recursive network? A resonator is a recursive network because it has a feedback path. If the comb filter is followed by a recursive network that has a number of poles that coincide exactly with the same number of zeros of the comb filter, we obtain a frequency sampling filter. The frequency sampling filter can be particularly attractive solution if we want to make a narrow band filter, right? So these are some of the applications of frequency sampling type of filter. Now, you understand what is a frequency sampling filter now? Okay. And this will result into lesser number of multipliers and adders. If you use the combination of comb filter and resonator, the hardware resources will be reduced. Okay, now let's look at one more. For practical application, we have to keep an eye on a number of things. In theory, we start by assuming that a number of poles and zeros coincide exactly on the unit circle in the Z plane. This requires that we should be able to realize the filter coefficients. This is important because the pole and zero should exactly coincide with each other. If the pole location is disturbed by some value even, then the cancellation of the pole and zero will not take place. And if the pole goes outside the unit circle, the system can become stable. And IIR filters, are little unstable filters. We have to be very careful in designing IIR filters, but I will explain you about IIR filters when we come to that part, right? But at present, we are designing FIR filters only. This requires that we should be able to realize the filter coefficients to an accuracy of 100%. However, apart from a few obvious exceptions, such as this is never the case. So we can manage the thing. This means that while we can locate the zeros of the comb filter section in exactly the right position, we cannot do so for because the best we can do is to get them in the vicinity. So this is just the more practical application of how to implement the system. In practice, both zeros and poles are therefore deliberately located just inside the unit circle. For comb filter, just inside the unit circle, so that the system does not become unstable, but the theory remains the same. And for comb filter, the system function is then chosen as with a factor of A. A is made slightly less than 1 so that it can come little inside the unit circle. And then even if some disturbance occurs in this system due to environmental effects or whatever other effects, the system, overall system should not go towards instability. But these points that I have mentioned here, these are related to the practical implementation of the frequency sampling filter. So it is a FIR filter. Why it is FIR filter? Because the impulse response goes from 0 to capital N minus 1. It is a finite response. It is a causal response, as I explained in my first slide. This is the example of an FIR filter, but it can be realized through a non-recursive approach also, but it has to be in combination with a comb filter and a resonator. That's very important. All right. So that finishes the frequency sampling filter. But before I finish my lecture, I want to explain, because we were in my previous lectures, I was doing the window function, windowing method of FIR filter design. One of the windows is very important, and that is known as Kaiser window. And this is the formula for Kaiser window, right? No need to go into the details of how this formula to derive, how to derive this formula, but this formula is there. We have to straightway take this formula. Why I am mentioning it here? Because what is small n? Small n goes from 0 to capital L minus 1, right? With a step of 1, where L is the window length, and capital M, because it's inside the formula, capital M appears. What is capital M? It is L minus 1 by 2. And I naught represents the modified Bessel function of the first kind. Why I'm mentioning it here? Because yesterday I did one of the practicals in one of the labs, and there we designed a band pass filter using Kaiser window. And you must know how to design a band pass filter. So that's why I brought some slides from there only. So this is the Kaiser window, very efficient window to design, and this reduces the Gibbs phenomenon to a great extent. All right. While writing the Matlab code, I explained in my practical class also, you have to use two functions, FIRL and Kaiser ORD. I have given the explanation of these functions also. You can read the how to use these functions. Okay. This is about the Kaiser ORD. And this was the problem actually I gave to these students to solve for a bandpass filter. A bandpass filter will have, let me show you the graph of the bandpass filter. Okay, this is a bandpass filter. A bandpass filter will have two passband frequencies, because one passband frequency will be on the left side, lower passband frequency, the other will be upper passband frequency. And there will be two stopband frequencies also. One stopband frequency, lower stopband frequency on the left, and other will be second stopband frequency for the on the upper side, on the right side. Okay. So this was the problem. This 0.5 dB is the passband attenuation levels, where we consider till this time the attenuation, the amplitude is from 1 dB, from 0 dB to 0.5 dB. We consider it to be in passband, and if it goes further down, then it will be taken as attenuation. All right. This is the passband attenuation given. This 35 dB is the stopband attenuation. This is the first passband frequency, second passband frequency, first stopband frequency, and second stopband frequency. And this is sampling frequency given is 200 radians per second. And the problem given to the students was to write the Matlab code. So this is the code. One of your students actually sent this code, right? So I'm using the same code what she has sent to me to share with everybody of this class, so that you can also run this code and design a bandpass filter using Kaiser window. If you find any difficulties, you can ask. And this is the output of the bandpass filter design. Or what are the specifications of this filter? These are the specifications of this filter. I just wanted to make 2-3 slides here to show you 2-3 slides here, so that you can understand how to design the filter using the Kaiser window. Okay, I finished my lecture here, and what I have done is the frequency sampling filter using comb filter in combination with the resonator. Thank you so much for joining. And if you have any questions, you can either ask now because we have 1 or 2 minutes, or otherwise you can email me, you can call me, no problem. Thank you so much.